Next is buffer solution. Can you hear me? Anybody please respond?
Yes, ma'am.
Buffer solution, no doubt, a solution which resists the change in pH. The solution which resists the change in pH. The solution which resists the change in pH. On addition of small amount of acid or alkali, small amount of acid or alkali are called buffer solution. Are called buffer solution. BUFFER, buffer solution. Example: blood, urine, etc. Blood, urine, etc. See, sometimes we take lemonade, acidic, but the pH of our blood is not changing. Sometimes we take basic fruits, for example, papaya, basic things we consume, that will not change our pH. So blood can resist the change in pH. Even if you take small amount of acid or small amount of alkali, the pH of the blood will not change. These solutions can resist the change in pH. Such solutions are called buffer solution. In chemistry, a mixture of a weak acid and its salt can act as a buffer solution, or mixture of a weak base and its salt can act as a buffer solution. Let's see how this buffer action is seen in chemistry. A mixture of weak acid, for example, CH3COOH. For us, weak acid means CH3COOH. Weak base means NH4OH. Its salt, that is CH3COOH. A mixture of weak acid and its salt can act as a buffer mixture, yeah, buffer solution. Similarly, a mixture of weak base, that is NH4OH plus its salt, that is NH4CH. This mixture can act as a buffer solution. How these mixtures can act as buffer solution? What is the buffer action? To the top one, if you add a little acid, it will resist the change in pH. It will not be acidic, the mixture will not be acidic. If you add a little amount of base into that, the mixture will not be basic. Similarly, in the second case, if you add little acid, it will resist the change in pH. That means it will not be acidic. If you add a little bit of base, it will not be basic. Means it will not change the pH. How this buffer action takes place? So let's take these two mixtures and add and see little bit of acid and base. So here, CH3 COOH plus CH3 COO minus Na plus. So this you are adding little bit of acid and little bit of base. Little bit of acid and little bit of base. Now HCl can provide H plus. H plus will react with this portion. That is, this is a strong electrolyte. This is a strong electrolyte. It dissociates fully. These lots and lots of CH3COO minus will be obtained. This CH3COO minus will react with this H plus to form CH3COOH, which is unionized or will be ionized. This is unionized. So I am writing that this H plus added will react with CH3COO minus to form CH3COOH, which is unionized. Ionized. You know that it is a weak acid or weakly ionized. Okay. Now, if you add a little base into that, this base will react with this portion. H plus reacted with this portion. Base will react with this portion to form water. Water means H plus from here and OH minus from NaOH to form H2O. H2O is also a weak electrolyte. We can say ionized. Ionized. Now we are going to the second mixture. That is a mixture of weak base and its salt. So I am writing this NH4OH plus its salt, that is NH4Cl. So this mixture, if you add little HCl or little NaOH, how it resists the change in pH? Suppose we are adding HCl, that means that H plus, this acid H plus will react with this OH minus. H plus reacts with this OH minus to form water, that is ionized. Now here, from here OH minus will react with NH4 plus. NH4Cl is a strong electrolyte, completely ionized, 100% ionization. So here OH minus will react with this NH4 plus and OH minus to form NH4OH, that is weakly ionized or unionized. So ultimately, nothing happens. So this mixture can resist the change in pH. So here, this mixture, that is a weak acid and its salt, or a weak base and its salt, can act as a buffer solution. Next, we are moving to the last term, solubility product. Solubility product. It is similar to an equilibrium bond state. This is for partially dissociating or sparingly soluble solid. For example, this calcium carbonate, precipitate only, solid only, calcium carbonate, when put in water, it is sparingly soluble. We consider it as insoluble, still we say, in the language of chemistry, we say little bit. If you put 100 calcium carbonate, 2 will be getting dissociated. That means 2 molecules will be soluble. Right? So, solubility product. Solubility product. This is for sparingly soluble solid. For sparingly soluble solid. Sparingly soluble solid. That means there can be an equilibrium between undissociated and the dissociated. Undissociated and the dissociated. The typical example is BaSO4. Precipitate only BaSO4. The solid, when put in water, very few BaSO4 get dissociated. That is, no. 100 if you put in 2 will get dissociated. You can say Ba2 plus X and SO4 2 minus X. Now, equilibrium between those things and these things, this thing. So, this Ka you can write, that Ka, this Kc you can write This Kc you can write, but this Kc is called Ksp. Solubility product Ksp. So Kc, first I write Kc. Kc is equal to Ba2 plus into SO4 2 minus upon this is solid, so you don't have to put in this equilibrium Kc equation. So this Kc I am writing it as Ksp, that is Ba2 plus into SO4 2 minus. SO4 2 minus. Ba2 plus, that is the solubility of Ba2 plus. Its conservation means the solubility. What is meant by solubility? The amount of substance that which is present, which is dissolved or which can be dissolved in a particular amount of solvent, or the amount of substance present in that solution, means per liter how much, these many moles per liter, that means molarity. So you can take this concentration in terms of molarity. Solubility, a concentration or molarity. So what is here, the molarity means the solubility. Here the molarity means the solubility. This much amount is present in this much liter of solution, or this much moles are present in this much liter of solution. So solubility means it is same as molarity. So that concentration I am writing S. So Ksp is equal to S, and this again S. So here Asp is equal to the same. This is the solubility, which is same as this thing. So like C alpha and C alpha what we have written. So Ksp is equal to S square. So you can find out Ksp has got a constant value for each and every sparingly soluble solid. BaSO4 has got a constant value, like the calcium carbonate got a constant value. So Ksp has got a constant value, that is the solubility product constant, you can say solubility product constant. So S square is equal to Ksp, so S square is equal to Ksp, or S is equal to square root of Ksp. You can calculate solubility, you can calculate Ksp. So these two things can be calculated by using this heading. If I take another salt, that is Zr thrice PO4 4 times. This is the valency of Zr and this is the valency of PO4. Valencies are interchanged, or you crisscross the valencies to write this molecular formula. But Zr, what are ions are present here? Zr 4 plus and PO4 3 minus. PO4 3 minus. These are the ions present in this. How many Zr 4 plus? Thrice. This is the valency of this thing. At the same time, this is the number of zirconium. This is this is the valence. This is the valency of zirconium. At the same time, it is the number of phosphate ion. Once again, this is the valency of phosphate ion. At the same time, it is the number of zirconium ions. This is the valency of zirconium. At the same time, it is the number of phosphate ions. So if it dissociates, how many zirconium 4 plus obtained? Thrice zirconium 4 plus and 4 times phosphate 3 minus. These are the ions in the dissolved condition. So I am going to write Ksp for this thing. Ksp is equal to, that is Kc, equilibrium constant Kc. Now we are calling it as Ksp for the sparingly soluble solid. This is 3s, 3 times S. This is 4 times S. Solubility is consumption. 3 times solubility S. then 3 times. Then what is Kp? That is this is the conservation. This is the conservation. So this raised to this 3, that is 3s to the power 3 and into 4s to the power 4 is equal to 9 and 27. 27 into 16 into 16. 16 into 16 into s to the power 7, right? Which is equal to 6, 9, 1, 2, s to the power 7, or solubility we can calculate. How can you calculate solubility? S to the power 7. S to the power 7 is equal to Ksp upon 6, 9, 1, 2, or S, that is 1, 7. Ksp, this is 7. 1, 7 Ksp upon 6, 9, 1, 2. This way, yes, you can write this 1, 7 as like this, raised to 1 by 7. So 1 by 7 log this. For calculation, you can utilize the log for this. By advantage. The solubility product of silver chloride is the solubility product of silver chloride is solubility product of silver chloride is, that is Kp. 1.2 into 10 to the power minus 10. No unit, just like Kc, no unit. At 290. Calculate the solubility of AgCl. Calculate the solubility of AgCl. Calculate the solubility of AgCl at 298 Kelvin. So AgCl is similar to our BaSO4. This in water Ag plus and Cl minus. So Ksp is equal to concentration of Ag plus and concentration of Cl minus, which is equal to S into S, that is S square. Ksp value is given, which is equal to 1.2 into 10 to the power minus 10. So S is equal to square root of 1.2 into 10 to the power minus 10 is equal to 1.1 into 10 to the power minus 5 molar solubility. Solubility means this much moles per liter of the solution. This is what is meant by molarity. Solubility means concentration. You can write in terms of molarity. Next question. Calculate the solubility of A2X3. Calculate the solubility of A2X3 in pure water. Assuming that neither kind of ion reacts with water. And hydrolysis, no further reaction takes place. Neither kind of ion reacts with water. Solubility product of A2X3. Solubility product of A2X3 has been equal to 1.1 into 10 to the power minus 1.1 into 10 to the power minus 2. So A2X3 in water, in water changes to twice A value is 3 plus, and thrice X value is minus 2. X times minus 2. So this is 2s, this is 3s. So Ksp is equal to 2s, this is the consideration, raised to 2 into 3s to the power 3, which is equal to 2 square 4 into 27 into s to the power 5. S to the power 5. Ksp value is given. What is Ksp value? 1.1 into 10 to the power minus 3. So, S to the power 5 is equal to 1.1 into 10 to the power minus 23. This is 108, or S is equal to 150. That is 1.1 into 10 to the power minus 23 divided by 108 raised to 155. The value is 10 to the power minus 5 moles per liter. Or you just write in this format only, this much smaller. You write in this format only, this much smaller, this much smaller. That is the solution. Now, what is the importance of the solubility products during the analysis? During the analysis means salt analysis. When you do the salt analysis in the laboratory, you haven't done any, but when you do cation analysis, cations are classified into different groups: zero group, first group, second group, third group, fifth group, sixth group, etc. In that, solubility products is applicable in the case of second, fourth, and three level of second and fourth. In second, CO2 plus cation is given. In fourth, nickel 2 plus or zinc 2 plus, cobalt 2 plus. So here, in the case of this second group ions, they are precipitated as CuS sulfide, they are NiS sulfide. We want the precipitate of these CuS or NiS, CuS in second group and NiS in fourth group. We want the precipitate. For that, the concentration that we are putting should exceed, that is called ionic product. The product of the concentration of the ions we are putting in the test tube, that ionic product should exceed its solubility product. There is a solubility product constant for the CuS. There is a solubility product constant for this NiS. If the concentration that you are putting in the test tube is greater than this, the solubility product. Solubility. This shows the soluble nature. If the concentration of these ions you are putting is greater than the solubility product, then the precipitation occurs. So when the ionic product you are putting concentration means that is called ion. You can take any amount of this product, any amount of this substance and add. Then you are deciding, so that product concentration is called ion. When ionic product exceeds this solubility product, when this ionic product exceeds solubility, ionic product means it is in your hand, what concentrations you are putting. But solubility product is constant. Now, this has got a low Ksp value. This has got a high Ksp value. So to precipitate CuS, you need less amount of CO2, less amount of S2 minus. To precipitate this, you have to put more amount of Ni2 plus and more amount of S2 plus. So how can we make that more amount in an equilibrium? To exceed that solubility product. To exceed the solubility product, ionic product that you are putting should be higher. When the ionic product exceeds the solubility product, for example, for this you are adding H2S. H2S is H plus dissociate in the form of H plus and S2. We have to exceed that low Ksp value of copper sulfide. Low Ksp value, there is only low, so we need only less amount of this S2 minus. But in the case of nickel sulfide, you need more amount of S2 plus because its Ksp value is higher. We have to exceed that higher value, so we want more amount of S2 minus. Here we need only less amount of S2 minus. So to have only less amount of S2 minus, we are adding HCl into this. So HCl gives a common ion effect. HCl gives a common ion. So H plus, then H plus when we put that will be taking some H2 minus and make this H plus. So the amount of H2 minus decreases. We need only less amount of S2 minus over there. Suppose we have more amount of S2 minus, then it may exceed NiS value. So NiS can be precipitated in second group. To avoid that, we keep S2 minus amount less. For that, we have to add a common ion. This common ion effect H plus to this. So H plus will be taking some S2 minus. So the amount of S2 minus will be less here. So ionic products, we need just to exceed that low value solubility. What about it? And Ni2 plus. In fourth group also we are getting H plus only. That is to H plus and S2 minus. Here we need more amount of S2 minus because NiS solubility product is NiS solubility product is high, so we need more amount of S2 minus. For that, we are adding NH4, OH. So this OH minus H will be taking away some H plus from here. So when this amount is less, more and more H plus will get dissociated to the right hand side. It will be moving to the forward direction. When it moves to the forward direction, we will be getting more and more S2 minus. So easily you can, with a high concentration of S2 minus, you can easily exceed that solubility product, precipitation will occur. So in second group, you need less amount of S2 minus. So you are adding H plus. The added H plus will be reacting with some S2 minus and go back, and then will be going back to form H plus. That means S2 minus concentration is very less. So with the less amount, you can exceed that solubility product because solubility product of copper sulfide is lower. That is in second group. In fourth group, solubility product of that NiS is higher, so you have to exceed that solubility product. That means you have to you need more amount of S2 minus there. To get more amount of S2 minus, you are putting NH4 OH there. From that OH minus will be reacting with that H plus and water will be formed. So H plus will be removed from this equilibrium. When H plus is removed, then what? According to Lee-Shanley's principle, more and more H plus will be getting dissociated. So you can exceed that solubility.